Okay, good. So we will be looking at so we are looking at graphical models, right? So we looked at belief networks, right? So we also said that we call Bayesian networks, Bayesian belief networks, etc., etc. And then we looked at the concept of causal, and then we looked at deseparation, right? So we looked at what deseparation is, and then I asked you about thinking about deseparation, and we also discussed what is the question of inference. So what is the question of inference? I will give you certain variables, certain observations. I can ask you questions about the conditional distributions. Given that the alarm rang, what is the probability that there was or given that Mary called, what is the probability that there was a earthquake, right? So those kinds of questions I can ask, right? If you think about this, so what are the questions I am asking in that case? They were all marginals, right? I have this joint distribution of Mary, alarm, John, earthquake, and burglary, right? There is 5 variables. So the whole system is specified by a joint distribution over these 5 variables, right? But I was asking you a question about a marginal, right? What is the probability that earthquake happened? Okay, that is a specific marginal I am asking a question about, right? So typically inference questions will be about marginals or conditional marginals, right? So conditional marginals will be when I am given some observation. Okay, given that Mary called, what is the probability of an earthquake? So that is a conditional marginal, right? So if I just ask the question, okay, nothing happens, what is the probability of a earthquake in California, right? So I want to ask that question, I can still do that, right? I can take this whole entire network, right, marginalize everything, I can tell you what is the probability of earthquake happening. That is not very interesting, right? Because it is already I give you the marginal as one of the components in specifying the network, right? All I can do is just look up the earthquake probability distribution, right? I already given you the marginal, that is one of the things that specify it, right? I can ask questions like, okay, what is the probability that Mary will call, right? I do not know anything else, just ask the question, okay, what is the likelihood that Mary is going to call me today, right? So I can just marginalize over all the other variables and I can give you that answer. So essentially queries are on some kind of marginals or conditional marginals. It could be joint distributions as well, it could be joint marginals as well, in the sense that what is the probability that Mary and John both will call me today. Right, so that is a joint distribution over a subset of the variables. So it is some kind of a joint marginal, right? So instead of looking at the full joint distribution. So those are the kinds of queries I am asking, right? So we looked at the directed networks, right? So today we will look at using undirected graphs. Look at undirected graphs and ouch, looks like a very complex graph, okay. So I am going to call these set of nodes as A, right? These 2 nodes are A, these 2 nodes are B. Just asking you, just grouping the random variables together here, right? So as before, each node is a random variable, just like we had in the directed case. Each node is a random variable, and the edge denotes some kind of dependence between the 2 random variables, right. So in the directed case you could confuse an edge for a causal relation, right. You could keep the edge as representing a causal relation, right, but here I removed the arrow, there is no direction here. So it is just some kind of dependence between 2 variables, right.
Like the single arrow was represented, instead of just one edges we have 2 edges, both variables depend on each other.
You could say that, but there is a slightly different semantics associated with the edges here, right. So see, the edges encode some notion of conditional independence, just like the edges there encoded some notion of conditional independence, the edges here also encode some notion of conditional independence, right. So, it is not like yeah, so there is a subtle difference between the two, right. So, I am not going to get into it because it is really subtle, but the class of conditional independences are different, right. There are some that you can represent using directed networks, there are some that you can represent using undirected networks. Most cases you can choose whichever you want, but there are some cases which is more convenient to go one way or the other, right. So, I do not want to get into the discussion, at least not in this class, it is for the class next semester if people want to get into do that, right. So, if you look at this, if I try to take any path from a node in A, right, if I try to take any path from a node in A to a node in B, right, I have to pass through some node in C, right. So, any path from A to B I will have to pass through some node in C, correct. Now, then I would say that C, the nodes in C separate the nodes in B from the nodes in A, right. Last time we had this notion of D separation, right, we had to write 3 different rules, right. D separation is nice for making up fun questions for exams, right, but it is a little confusing, right. So, you have all these arrows that you have to take care of. The notion of separation here is very easy. What it says is, if there cannot be any path from A to B which goes through, which does not go through C, okay, it is like I put a double negative there. So, every path from A to B goes through C, right, in which case then you say C separates A and B, okay, the D is gone here, right, it is just simple separation. Right, make sense, right. So, that is simple enough, right. So, this is what we started off with this notion of separation that is encoded in a directed model. So, in the undirected case I am telling you that separation is very simple, right, we had D separation here, we have separation here, right. So, next we have to think about something else, right. If you recall, when we started the discussion of directed models, we started off by looking at some kind of factorization of the joint distribution, right. So, we had a very complex, we had a joint distribution over many variables. So, we started looking at some kind of factorization of it, and from there we constructed the network, right. So, the graphical model inherently implicitly encodes a factorization, right. So, all this separation business in fact ties in directly to the factorization, right. So, the D separation gives you the rules for the factorization also, right. So, from a directed model it is very easy to write down the factorization, you just look at the conditional distributions and you write down the factorization. Here we really do not have such kind of a one way implication here, right. I am just saying something links the two variables together, right. So, how do we go about doing the factorization? Right. So, there is something, there is a concept called the Markov blanket, right. And I forgot to mention when we did directed models, right. So, a Markov blanket is essentially all the variables, right, that could potentially influence a given node, right. So, given the node the parents can influence the node, correct? Right, anything else? The children can influence the node, right? Anything else? Huh? Siblings can influence the node, right? Sibling, yeah. Right, so that is essentially the Markov blanket of a node, right? So I have a node, right? If I take node I, right? So this is essentially the right. This is right. So if I don't know the parent, then this node can influence this one, right? If I don't know the parent, this can influence this one. That's fine. Yeah. So this is essentially the Markov blanket of I, right? So what will be the Markov blanket in the undirected case? Huh? Same. Huh? It has to be directly connected. The neighbors of I. In the undirected case, it is just the neighbors of I. So if these are connected to other nodes, I do not care, right? So they cannot influence me except through this. Yeah.
But there can be a node that affects this node and this node affects this node.
No, I am looking at direct influence. So that node cannot directly influence me, right? So if I do not know this guy, right? So what is the thing? So if I yeah, so let me think about it. Okay. So this one. So if I know this node, right, these two get connected, right? If I know this node, these two get connected, right? So essentially that is basically it. So if I know this guy, okay, then I get connected to this guy. So if I just condition, if I say okay, I know this, I know this, I know this, I know this, right? Huh? Okay, so that is the Markov blanket of this I node I, and likewise here if I know these 4 guys, then that is it basically, nothing else will influence my I. So it will cut off from everybody else, right? These 4 nodes will separate I from the rest of the network, right? And here I need to know all of these guys, right, before I am cut off from the rest of the network, right. So you really do not need the Markov blanket, right? It is just an aside that I wanted to tell you. No, you need a Markov blanket for other things, but not for this lecture or for this course, right. So the Markov blanket is very important because you need it for doing inference later on, right. So I will clarify the thing, but so essentially the idea behind the Markov blanket is once you know all of these nodes, right, you are completely separated from the rest of the graph. Yeah.
Why are the bottom 2 nodes in the Markov blanket? The children I got, yeah, the other 2.
So if you know the children,
Yeah.
then these two get linked up, right?
No, but if I know the child, I don't really care what the other node is, right?
No, see if I know the child,
Yeah.
right, then the probability on I, right, so if you remember the third deseparation rule we had, right, if I do not know the child, then these two are independent, right. If I do not know the child, then these two are independent because there is no way information can go from one to the other, but if I know the child, then these two get linked up. So we will go back to factorization now. consider two nodes xi and xj such that there is no direct link between xi and xj, right. So something like this, right. So this could be xi, that could be xj, so there is no direct link between them, right. Let us say that the set x denotes the inverse of all variables, right. So it has x1 to xp, so set x denotes all the variables, and if I condition the joint distribution of xi xj on everything other than xi xj, right. So what can you tell me about this distribution? This should factor out, right. So people have not encountered this before, that is the set difference, okay. So people are getting confused by that, that is the set difference, right. So this I am from x, I am removing xi xj, so conditioned on that, right, they should be independent, right, conditioned on the rest of the variables. What essentially I am saying is, okay, xi and xj, I am conditioning it on everything else. So every path between xi and xj has to go through, well, everything else, right. So I have conditioned it on that, so they have to be independent. So that is the basic assumption I have, right. The factorization that I am assuming here is that the conditional independence thing is, if all paths from A to B pass through C, right, then A is conditionally independent of B given C. So here my C is everything other than xi xj, so this has to be true. So if you think about it, now when I write my factorization, right, when I am going to write what I mean by writing my factorization, I am going to take my probability of I am going to take this joint probability and I am going to write it as some factor 1 on some set of variables right. So like this I am going to write it out like this, right. This is what I mean by factorization, right. In the directed case I also did the factorization, except that my psi had a very specific form. My psi would have been something like, what is the probability of x1 given x2 comma x3, right. So that is a factor, right, and my psi 2 could have been, what is the probability of x3 given x4 comma x5, that is another factor. So like that I could have written out multiple factors in the directed case. In the undirected case I have to figure out what these factors are going to be. In the directed case I already have figured it out, in the undirected case I have to figure out what these factors are going to be, right. So we want this to hold, right, we want this conditional independence to hold. So what can you say about the factors? If there is a factor that directly connects x1, xi and xj, if there is a factor, right, in all this factorization I have, there is some factor that has, I have some factor like that, right. So now there could be some assignments of these, some kind of derivation of these factors which will connect xi and xj, right. So I cannot say that xi and xj will be independent, right, regardless of what values I am assigning to the factors. If there is a factor that actually has xi and xj in them, right, then I can't be guaranteed of this independence for all assignments to those factors. The only way I can ensure that this independence will hold is if I guarantee that xi xj will not appear together in any factor. So I cannot have a psi function here in the set of factors that I write, I cannot have a psi function that has both xi and xj as arguments. Right? Is it clear? The reasoning clear? If xi and xj appear in any one of these size together, right, then I can assign some values to the size such that those two get connected. Right? So, to make sure that I can never do that, that this conditional independence holds for all possible distributions I can write. Right? So, I will have to make sure that there is no factor right, no factor should contain xi and xj. Right. So, I am going to take this intuition, right, and flip it around. Right. If there is no edge between xi and xj, then no factor should contain xi xj. Right. If there is an edge between xi and xj, there should be a factor that contains xi xj. Right. I am flipping it around. If I want to encode the dependence between xi and xj, there should be a factor that contains xi xj. Suppose there is an edge between xi xj, xj xk and xk xi. So, what would you want to do? You can put in factors for every edge, right. Alternatively, a more compact way of doing this is to put in a factor for the clique, right. So, if you have some set of variables which are fully connected, then you will put in a factor for all of the variables together, because there is this three-way dependence, right. So, instead of putting in as 3 different factors for that, you put in a single factor that looks at all of this together, right. So, flip this around and then say that for you want me to repeat what psi represents? Because I didn't even say what it represents, but I will tell you what it represents. But the thing is, it's just some factor, right? In directed models, right, psi was the conditional probability. So essentially, I am taking one complex function, right? I am taking this p of x1 to xp, right? Okay, so I am taking this function, right? That is a very complex function. I am writing that out as a product of many smaller functions. Right, each of this psi is a one such function.
So xi and xj occurring
values, and if we make phi 1 of equal to some constant, then x1 and x2 are dependent. Do we say? Can we say that? Like that?
I didn't get what you are saying. So everything else is a constant, and then yeah.
Function of x1 and x2.
Okay.
If we now it's a function of two variables. If we assign phi 1 of x1 x2 equal to some constant, then x1 and x2 becomes dependent. Do we mean to say by dependence of x1 and x2?
Sure. Yeah. So that would be the case, right? So when I'm conditioning on every other variable, that means I'm essentially assigning a value to every other variable. So all the other factors will reduce to some fixed value, right? And then I'll have only x1 x2 left, right? Even then, my choice for x1, right, would depend on the choice for x2. So that's one way of interpreting that. Yeah, right. So people got his way of looking at it. He says if fix all the other values, right. So let us assume that psi 1 has x1 and x2, and x1 x2 don't appear in anything else, just for simplicity's sake, right. So if fix all other values, so everything else will reduce to a constant. Right, so it will be psi x1 x2 times a constant, and I am looking at the probability. Right, now whatever value I choose for x1 will depend on x2. Right, the probabilities assigned for a value of x1 will depend on what is the value I have taken for x2. There is a way to make it independent even then. Right, so I can just give the same value for same probability for x1 equal to 0 when x2 equal to 0 and when x2 equal to 1. Right, so I can assign the same probability. There is a very specific assignment that can make it look independent. So something like this, right. Right, so what is the probability that x1 is 0 right. So I am conditioning it, right. So the conditional probability I can say that, okay, so this is 0.2, this is 0.2, this is 0.8, this is 0.8, right. Now x1 is independent of x2, even though I have a factor psi x1 x2, say, but x1 is independent of x2, right. But I have to be very careful about actually assigning the values to the factors, right. So what we are trying to do is give a factorization that regardless of what function we choose for psi 1, right, it will end up being independent. If I condition on everything else, it will be independent. So I can put in whatever random numbers I want there, okay. I still want x1 to be independent from x2, so that can't be the case if there is a factor that has x1 x2 in it.
So the last sentence here I wrote that for each clique there exists a factor or have a factor.
Yeah, for each clique you have a factor in this, yeah. You put in a factor, so you are designing how the factorization should be, right. So I am just saying for each clique you include a factor, yeah.
So you have 0.2, 0.2, 0.8, 0.8, right?
Yeah.
So then it won't be independent.
Well, the other way around. So x2 is independent of x1. No, no, it's correct, right? x1 is independent of x2, right? So whether x2 is 0 or x2 is 1, right? So it does not matter, right? So what is the probability of x1 equal to 0 given x2 equal to 0, right? So that is equal to the probability of x1 equal to 0 given x2 equal to 1 is equal to the probability of, right? So it is independent, right? Huh? No, I said it's conditional, right?
But technically it is not valid.
Why? Why?
If we take given x1 equals to 0, probability of x2 equal to 0 is 0.2, x2 equal to 1 is 0.2.
No, no, no. This is writing. I am writing the conditional. I am only writing the probability of x1 given x2. I am not writing the joint distribution there. So each column should be a valid distribution.
Row as well.
No, no. Each column should be valid distribution. The row need not be. Row need not be. Why? I am writing the conditional, right? I am writing the probability of x1 given x2. So why should the rows be the
But the
distribution?
joint PDF should be valid.
It's not joint. I am just written the conditional. I am not written the joint. Yeah. So whatever. So to get the joint, I need to define a distribution over x2. Right. So which I have not done. I have just looked at one factor here. So you could have a factor over x2 if you want, but I have not done that. So,
Sir,
yeah.
what are we aiming to say here?
What are we?
What are we trying to say in this package?
So see, for the directed graphs, right. So you could easily write down what the factorization is, right. So I have some probability, the joint distribution. Remember, all of these graphs represent joint distribution over p variables, right. I don't know, p is hard. Let's make it n. Okay, I am going to make it. Right. So having probability as p and the dimension as p is a little confusing for me, right. So I have n variables, whether it's a directed graph or whether it's an undirected graph. So what I am trying to represent is the probability joint distribution over n variables, right. And the whole idea of going to this graphical models is that I do not want to define this whole n squared minus 1 number of values for specifying my probability distribution, right. So I want to say that, hey, no, really the probability distribution is not so complex. There are not n squared independent values in my distribution. So there is some kind of factorization that will happen, right. So I am truly trying to figure out which are the independent values that I have to specify so that I can get the entire probability distribution again, right. So for that I am finding out what is the right way to factorize my probability distribution.
Can there be more than one factorization?
Sure. There can be more than one factorization. Why what's the confusion, right. So if you think about even the directed models, right. So you wrote down one factorization, but you can always think of flipping the direction of the edges, right, and writing another factorization, right. So it's nothing to it, there is nothing very sacrosanct about this. The reason we choose this factorization is because it is easy to handle these things, right. So that is the only reason, right. And so in the directed graph we knew how to find the factorization, so we looked at the conditional independence. So in the undirected case, right, so we need to come up with some way of finding what the factorization is, right. So what I am saying is, so what are the things the factors should not have, that first if we characterize that, okay, then we can go and write down what should be the factorization. Okay, what are the things the factors should not have is that if there is no edge between two variables, they should not appear together in a factor, right. If they appear together in a factor, then that is a way of assigning values to the factor, right. So here, so if you think about it, this is actually a factor in a conditional in a directed graph, right. This could potentially be a factor in a directed graph, right. So for example something like this, right. Right, so this could be it, right. But now even though I have written this dependence factor, I have assigned values here so that the dependence does not hold, right, but I can assign something else here, right. So then this equality is broken. So if I have a factor that has both x1 and x2 in it, when I write this factorization, then it is possible for me to assign some values so that this independence does not hold. So when we are talking about these factorizations, what we are really looking for is a representation, okay, that regardless of the numerical values you eventually end up assigning to it, preserve the independence relations that you are looking for. Right? They may introduce additional independence relations, but at least the ones that you guarantee should be there in the probability. So when the graph guarantees something, the graph structure guarantees some independence relation, okay, the factorization you give should guarantee that independence also. So if I put in a factor that connects x1 and x2, when there is no edge between x1 and x2, I can no longer guarantee that. So that is essentially what we are trying to look at, right. So any other questions? I know it's always a little tricky when you move to undirected graphical models, right. So directed graphical models are all very easy, right, everyone gets it the first time around. So undirected graphical models are a little confusing, right, and it's good to look at them from the very beginning because a lot of the techniques that we use for inferencing, right, are in some sense common to both directed and undirected models, right. So if you understand the two models as something common, right, having something common in between them, then all the techniques that we look at afterwards, okay, I can just talk in one language. I do not have to do inference techniques for directed models and then go back and do inference techniques for undirected models, right, they are all the same, right. Operationally there might be, so like implementation wise you might do some things little bit more efficiently if you know that you are working only with directed models, right, or if you know if you are only working with undirected models, but the algorithm wise it's pretty much the same, okay. So let us spend a little time and try to understand undirected models. So any questions on this so far?
Can we say we should not have a xi which connects xi and xj conditioned on the variables in C?
Condition, no, we should not have a factor xi that connects xi and xj, that have both xi and xj as an argument.
These are independent only in the case where we fix C.
Yeah.
So we can say.
But I can assign values, that is what I am saying, right. I can always assign values to that function xi such that they become connected. See, the whole idea of giving a factorization is regardless of what you do with that psi, right, you can do whatever you want with the psi, but I still want to guarantee the independence. So as soon as I put in xi and xj in the same function, I give you the freedom to do something with that function to introduce the dependence. So we do not want to give the freedom to the process by which you are determining the values for the psi functions. So that is the restriction that we want to introduce here. Okay, great. So I am flipping this around. Since we say that if there is no edge there should not be a factor, then I am saying that if there is an edge there should be a factor, right. In fact I want to go a little further and say that if there is a clique, right, there should be a factor associated with the clique, right. So better, right. So let us Suppose I have a graph like that. So, I have 4 random variables, right. So, what should be the factors here? I should have something that connects 1, 2, 3. Something that connects 1, 2, 3, 4, is it? I should have something that connects 1, 2, 3, 4. Why? It is not a clique, right. So, 1, 4 is not connected, therefore, I do not want a factor that has 1 and 4 in it at the same time. I cannot have a 1, 2, 3, 4 factor. So, it can be 1, 2, 3, 2, 3, 4, anything else? Right. So, you automatically made my point for me, right. All I need to consider are maximal cliques, right. If you think about it, 1, 2 is a clique, right, 2, 3 is a clique, 3, 4 is a clique, everything is, each edge by itself is a clique, right. So, you didn't give me factors for the cliques, you gave me factors for the maximal cliques, right. It turns out that if you introduce factors for the maximal cliques, you essentially have the same representation power as having factors for all the cliques in the graph, right. So, you can restrict it to so in this case it is that and that. So, we have only 2 factors here, okay. Is it clear?